As the title says, this chapter is on hydrological exchanges and heat exchanges. So Peter takes a different approach in this book in terms of organizing the flow of topics. Here we are going to look at the freshwater flux between the land, ocean, and the atmosphere, and then heat exchanges between the land, ocean, and the atmosphere. Mostly we'll focus on the ocean heat exchange, not so much the land. We'll come back to land later on. Some scientific trivia kind of information, looking at the relative areas of land and ocean here in million square kilometers, zonal mean latitudinal distributions, along with the sea surface temperatures. We know that the sea surface temperatures are warm in the low latitudes with a slight asymmetry, hemispheric asymmetry, because of the land-ocean contrast, which you can see clearly here, as well as at the mid-latitude to polar latitudes here. So you can see this one is a much flatter, longer tail here from the mid-latitudes towards the Antarctic continent, because of the unique configuration of the Southern Ocean, whereas here you have the complicated North Pacific, North Atlantic, the land-ocean contrast leading into the Arctic. In terms of the total surface area, ocean obviously occupies 70% on average, with varying distribution. So you can see the Southern Ocean and Antarctic continent impacts here, and the Southern Hemisphere land being much smaller than the Northern Hemisphere land area, which typically has been invoked for the asymmetry in the ITCZ, but we will see that there are actually different theories about it as well. Just in terms of the fluxes of water and water cycle, terrestrial atmosphere, marine atmosphere, so you can distinguish the atmosphere over the land and oceans themselves, and land itself. So you can see that the residence times vary, so terrestrial atmosphere cannot keep the water for too long, average of 15 days. Over the marine atmosphere, the residence time is slightly shorter, of 10 days, because of the various dynamic processes that take the moisture and then create rainfall out of it, and land vegetation, evapotranspiration involved as well. In the ocean, it depends on where you are. In the surface, you have a water parcel with a residence time of about 100 years, and in the thermocline and abyssal oceans, it can vary quite a bit. So we are also looking at the water reservoirs here in terms of petakilograms, so 10 to the 15 kilograms. The main things to notice, of course, is that the evaporation and transpiration from land put water vapor into the atmosphere of about 71 petakilograms, and precipitation is 107. So land gives that back to the ocean as river runoff of 36, which is the difference between these two numbers. And obviously the marine atmosphere, which receives a lot of evaporation from the ocean, infinite source of water vapor for evaporation from the oceans. A lot of it falls back on the ocean itself as rainfall, obviously, but this amount that's coming off as runoff is balanced by what the advection of water vapor from the marine atmosphere is onto the terrestrial atmosphere. So that's the excess rain that terrestrial atmosphere receives. So the reservoirs there, 10 to the 15 kilograms, and fluxes of 10 to the 15 kilograms per year. I hope the concept of reservoir and flux are clear. So simply here, reservoir is what's in the stock of a particular sector, let's say atmosphere over the land or ocean, and land itself and ocean itself. And flux, of course, when you integrate over the whole globe, it's just per time, but often when we look at evaporation and precipitation to do balances, we will see that it'll be mass per area per time, so it'll be something like kilogram per meter squared per month or per year, and so on. Okay, simple things. Looking at rainfall rates, again, interesting things to look at. I will just point out one or two things. So this is looking at annual means and the solstitial and equinoctial seasons in 10 to the 11 meter cube per day. So these are massive numbers, so you have to be careful to remember that these differences, which may look like they are small, are actually not that small when you remember it's 10 to the 15 kilogram. The same, for example, here, ice and snow store 43,400 times 10 to the 15 kilogram, and the surface water is tiny compared to that, just 360 times 10 to the 15 with a residence time of 5 years. Subsurface, obviously there is a massive storage of 15,300 petakilograms with 1,000 to 10,000 year residence times, and a storage of total of 59,000 there. Okay, so the difference to note here, of course, seasonality is there when you look at the global rainfall, and ocean receives much more than land. The range, a seasonal range here, goes from 2.95 to a maximum of 3.39, which is about 0.43 times 10 to the 11 meter cube per day, which is pretty large. Whereas the range on the ocean is from like 10 to the 35 to the 10.35 to 10.55, so it's 0.2. So the seasonal range of global mean rainfall or the global mean rainfall is smaller on the ocean compared to land because of these transport of moisture needed. And there are asymmetries in the hemisphere as well, as we already saw. And the southern hemisphere has less land, but you can see that it receives more rain because it has more ocean, which can put more moisture on to land. And the June, July, August of the northern hemisphere has the largest amount of rain in these hemispheric land ocean distributions and the seasonality. So the seasonal cycle there is also pretty large. Basically, the hemispheric monsoonal circulation creates those contrasts. We will come back to this. Basically, we are looking at the Clausius-Clapeyron relation. People who know enough math know that when you have ddt, this is water vapor, partial pressure of water vapor and temperature, and you have ES here, saturation water vapor. Obviously, this means an exponential relation that is related to latent heat of exchange, evaporation and condensation, and sublimation and deposition. I should have turned these into subscripts, but anyway, you get the point. So these numbers of the exchanges for evaporation, condensation, and sublimation, deposition are here 2.5 times 10 to the 6 joules per kilogram and 2.84 times 10 to the 6 joules per kilogram. And the latent heat of freezing or going from water to ice is 3.3 times 10 to the 5 joules per kilogram. Obviously, it turns out that water vapor is the most non-linear of all things in the Earth's climate system. RV here is the gas constant because air basically is an ideal gas, so we can use the ideal gas relation to simplify certain things or move between temperature and pressure and so on. We will see that later on when we come to dynamics. But you get the point that this nonlinear dependence of water vapor on temperature, exponential dependence, makes for very interesting behavior of the Earth's climate system. We will see that in the next podcast. We'll build on this Clausius-Clapeyron relation throughout because it is one of the most interesting thermodynamic process in the Earth's climate system.